So I thank organizers for giving me opportunity to present my work. So that I'm going to talk about engineering antiferromagnetic skyrmions and antiskyrmions at metallic interfaces. So this is outline of my talk. So first I will introduce about the magnetic skyrmions and their antiferromagnetic counterparts and double exchange model. Then I will derive an effective spin only model from spin fermionic model. Then I will show some results and summarize it. So this work is published in these two PRB papers. So first, magnetic skyrmions are stable topological magnetic textures, which like for example, we see Neal skyrmion where central spin is down, and as we move outward, the spin moves point out in up direction. So we can basically, this is the historiographic projection of this object. And there are other similar objects or some distinct like block skyrmions and antiskyrmions. So we classify these objects by this quantity called topological charge, which is basically the integral of this thing. And here spin have three components, and where this integration is happening in the two-dimensional plane. So this quantity turns out to be an integer. Another quantity, which is polarity, defined by the direction of the central spin, or like here central spin is down, so polarity is -1. So when Q and P have same sign, these are called skyrmions, and these when opposite sign are called antiskyrmions. So there are another objects called antiferromagnetic skyrmions. So these are basically the superposition of two skyrmions of opposite polarity or opposite topological charge, and these are considered to be more superior than the skyrmions. The reason behind is that when a material with whole skyrmions current passes through, then the skyrmions experience a transverse deflection, which is called skyrmion Hall effect. So because of these, this is a superposition of these two, it doesn't experience the skyrmion Hall effect. So the antiferromagnetic counterpart of antiskyrmions are called antiferromagnetic antiskyrmions. So there are various class of materials where these all kind of textures are found. So let's start with a very simple Hamiltonian, which describes a system with localized moments coupled to the itinerant electrons that can hop to the nearest neighbor sites. The Hamiltonian is, there is tight binding term, and there is a coupling between localized moments and classical spins. So here Hamiltonian is global Z basis, so electrons can hop from up to up and or down to down. So now what we do, we transform this Hamiltonian. So first thing is that these spins are a large magnetic moment, so we consider them to be classical spins. So now what we do here, we transform this Hamiltonian using this unitary transformation, such that the new basis, the Hamiltonian transform into new basis, such that the electrons can hop to nearest neighbor sites with either aligning parallel or anti-parallel to the localized moments. So the advantage of this thing is that this term in the Hamiltonian becomes diagonal. So we get the two bands of parallel or anti-parallel bands. So in this picture, when Hund's coupling is very large, this anti-parallel band is very far away. So the ground state energy of metallic system can be understood with the low energy lying parallel band only. And the advantage of this is also that from this Hamiltonian, we get a very simple looking Hamiltonian, which looks like tight binding Hamiltonian. Only difference is now T hoppings are not constant but are dependent on the localized moment sites. So now we propose a model here to get antiferromagnetic skyrmions in the system. So this model has a bilayer model where we consider a metallic layer with spin orbit coupling and insulating antiferromagnetic layer. So here in the antiferromagnetic layer, there is an exchange interaction of antiferromagnetic interaction between the localized moments, and there is a Hund's coupling between the localized moments and the electronic spins. And here we consider the type of spin orbit coupling, which is Dressel-Haus spin orbit coupling, which occurs in systems because of the bulk inversion asymmetry. and its expression in continuum is given by this. So we now write the lattice version of lattice Hamiltonian on square lattice. So here it has electronic part and there is a classical part. So electronic part consists of tight binding terms, the spin orbit coupling terms, and you can see here the electrons can hop from up to down also, or down to up. And there is a Hund's coupling. The classical term in Hamiltonian are antiferromagnetic coupling and Zeeman field. So similarly, using the unity transform, we can now again transform this Hamiltonian to get a very simple looking Hamiltonian where these projected hoppings are given by some of these hoppings, and this we work out, and the expression for these are given by this. So now we can simulate this Hamiltonian. So with this, since this Hamiltonian is an electronic Hamiltonian with the classical spins are also present, we need to simulate this by using classical Monte Carlo simulation and the combination of classical Monte Carlo and the exact diagonalization, which is called hybrid Monte Carlo simulation. And so here are the results. For zero antiferromagnetic coupling, we can see occurs the anti-skyrmions in the system, and for finite JF at some parameter regime, we find antiferromagnetic skyrmions, antiferromagnetic anti-skyrmions. And we also plot here the skyrmion density map for these objects, and the skyrmion density is basically is the sum of the local skyrmion densities, and the local skyrmion density has this expression, which is the lattice version of the topological charge I showed in first slide. Now we can so these results, for simpler understanding of these results, we derive an effective spin Hamiltonian out of this. So how we do this? Basically, the projected hoppings can be written in polar form, where this is the radial part and this is the argument part. So now to integrate out the electrons, we calculate this coupling constants in the ground state of the system, and these are complete constants such that the Hamiltonian becomes this, where Dij and Fij are present. So we worked out this calculation and found the final expression for Fij along x and y directions look like this, and where the isotropic Heisenberg term and DM-like interaction term and their cation-like term occurs naturally in this Hamiltonian. But now here coupling constants are not in general are uniform. So what we do, we checked that in our system in the ground states, the various states we find that we check that the coupling constants can be approximated to be uniform, such that we take this to be a constant for d naught, and which for simulation purpose we use d naught equals to 1. So in this way we get from spin fermion model to finally a spin only model. So with this spin only model we can do classical Monte Carlo simulations, and where this Fij expression is this. So first we simulate this by classical Monte Carlo simulation for the case when antiferromagnetic coupling is 0. So the Hamiltonian is this, and we put Dij equals to 1, and this Hamiltonian for Dresselhaus case is this, which looks similar to the case of Rashba metals, which Sanjeev also talked about in his talk. So I am showing here the classical Monte Carlo simulation results in form of movie, where the movie is made out of the various spin configuration snapshots taken at each Monte Carlo steps. So this is this result movie I am showing for the Rashba case. The result will be same for Dresselhaus. So let's see movies. Yeah. So at high temperature, at spin orbit coupling 0.35 and some Zeeman field, we start with a paramagnetic state and start cool down the temperature, cool down the system, and you can see that skyrmions start to form here, and at very low temperature we can clearly see the skyrmions. And there is another calculation with the zero field cooling protocol, where we do simulation at some finite spin orbit coupling and ground state at low temperature, where at zero field we see these domains like structures in as the ground states, and now we start increasing the Zeeman field here, and so we can see that skyrmions are forming around this nuclear center of the these domain walls. And as you can see that as the Zeeman field increases, the skyrmion sizes decreases, and at very large Zeeman field, the skyrmions basically system goes to saturated ferromagnetic state. So finally they disappear. So now in our Dresselhaus Hamiltonian, we just what we have done, just flip the sign of the one of the hopping parameter. So the consequence of that will be that we get this Hamiltonian now, and we simulate this Hamiltonian also. Then we see that this domain walls with increasing Zeeman field, we get, instead of antiskyrmions, we get block skyrmions, and at large spin orbit coupling, we get a packed arrangement of these small size block skyrmions, and at very large spin orbit coupling, we get a smallest possible block skyrmions. So what we are doing, why we are doing this, what we conclude from this, that when hopping parameters have the same sign, the relevant energy band of the material will have the minima at gamma point. But when there is a opposite sign or relative sign difference between the hoppings along x and y, then the relevant energy band that crosses the Fermi surface will have gamma point, will have minima away from the gamma point. And so we conclude that the material for which the minima lies away from the gamma point, in those materials the block skyrmions should be present. And this indeed is observed in various materials in experiments also. So now here I show here the dependence of various magnetic textures on the type of spin orbit coupling, Rashba or Dresselhaus, and the relative hopping parameters between Tx and x and y direction, and we get Neal skyrmion, block skyrmion, and these two type of skyrmions. So yeah, so this is a result I've shown for finite antiferromagnetic coupling case in form of a phase diagram, where for these parameters we simulate again the classical Monte Carlo simulation for the effective spin Hamiltonian, and here I show the phase diagram between JF and HZ. And so here the interesting phases are this filamentary domain or wall structure, which is lies very for small JF and small HZ. At when we increase in magnetic field, Zeeman field, we see the packed antiskyrmion state. So the packed antiskyrmion state, so in our effective spin Hamiltonian, there were 3 terms, and there is another term JF. So these compete. So this JF term competes with the isotropic Heisenberg term, so which results in this packed antiskyrmion state for low values of JF. And we also observed that in this state region of the phase space, as we increase the JF, the skyrmion size decreases, which means that JF act as an additive factor to the spin orbit coupling also. So at intermediate regime, we see we can the effect from effective Hamiltonian, we can say that JF almost cancels the isotropic part, which results in the skyrmionic square lattice arrangement of antiskyrmions. And at large JF regime, in this region of phase space, we get the antiferromagnetic antiskyrmions, because JF is very large, and this combines with the DM interaction term also, that results in the antiferromagnetic antiskyrmion phase. So here I am showing the classical Monte Carlo results, where at this regime, this is the state is anti-skyrmions, which are packed arrangement. Now, and this region, there is antiferromagnetic antiskyrmions. So, so to see this state clearly, I have shown also the sublattice resolving of this spin configuration, and we can see that this spin configuration is a superposition of two type of skyrmions. So this is antiskyrmion is central spin is up, and this has down. So opposite polarity antiskyrmions superimposed to get this antiferromagnetic antiskyrmions. So with this, I conclude, summarize the talk. And so we have seen that antiferromagnetic counterpart of skyrmions and antiskyrmions can be stabilized at the interface between antiferromagnetic insulator and spin orbit coupled metal. And these exotic magnetic phases were stabilized by long range interactions mediated by conduction electrons. So the electronic literacy also plays very important role in determining the magnetic textures, and the JF plays the role of additive factor to spin orbit coupling. So this work I did with Sanjeev Kumar and Anna Mukherjee. So I thank them, and I also thank the audience here.
Thank you, Deepak, for finishing on time. Questions? Comments? Questions from the online audience?
Yeah. So you focused on classical spins.
Yeah, so we consider them to be classical.
What about quantum spins?
So for that,
Will it lead to quantum spin liquid?
So we are dealing with we are explaining the systems where there are basically large atomic moments for localized moments. So
I understand.
the electrons
but
are.
I'm saying that. Have you thought about?
No, means I have not.
Because it seems to be a way to go to chiral spin liquid when you have a skyrmion liquid. We can discuss it. Yeah.
Yeah.
Thank you. If there are no more questions, let's thank Deepak again.